Hello Math 122, welcome back to the second video that I'm producing for you. So this video is on section 4.2, which is all about inflection points, the natural continuation of the local extrema that we talked about in the last video. So remember from last time that a local extrema was defined to be a point where the first derivative changed sign. So that first derivative could change from positive to negative, or it could change from negative to positive. But as long as that sign changed, we said that the point at which that occurred was going to be called a local extrema. And remember that point could either be a local minimum or a local maximum, depending on whether the sign changed from positive to negative or from negative to positive. So it's natural to ask the question, if we have a special name for points where the first derivative changes sign, do we have a special name for points where the second derivative changes sign as well? And in fact, we do have a special name for these points. So these are called inflection points. So a point at which the graph of a function f changes concavity is called an inflection point of f. So the important thing to note here is it's a point where we're changing concavity. And another way of characterizing this change in concavity is saying that we have a point where the second derivative is changing sign. So remember that the second derivative and concavity of a function are closely related to one another. If the second derivative is positive, then our function is concave up. And if the second derivative is negative, then our function is concave down. So this change in concavity is equivalent to looking for a change in the sign of the second derivative. And below this, I have a couple of examples of inflection points that are showing up on two different functions. So this first function on the left is actually f of x equals x cubed, and there is exactly one inflection point where the function is changing concavity. And that inflection point is occurring at x equals 0. So if you look to the left of x equals 0, you see that the function is concave down, and then as we move to the right of x equals 0, the function is concave up. So the second derivative is changing from negative to positive, in this case at x equals 0. And the other function is f of x equals sine of x, which is a trig function that we don't necessarily talk about in this class, but it's a good example for identifying inflection points because there are a ton of them. So again, if you look at x equals 0, we have an inflection point, and the other inflection point is at x equals pi. So left of x equals 0, we're concave up. Right of x equals 0, we're concave down. And then again, as we go right of x equals pi, we're concave up again. So this function is changing concave up to concave down over and over again. And likewise, the second derivative is changing positive to negative over and over again. So looking for inflection points amounts to looking for changes in concavity in your graph. And similar to the local extrema from the last section, we have tests that we can use to determine which points are inflection points of our function. So suppose that the second derivative is defined on both sides of some point p. So if this second derivative is 0 or undefined at that point p, then we say that p is a possible inflection point. So it's not necessarily an inflection point, but these are the points that we're going to look at to determine whether or not they are inflection points. So the same way that we look for critical points first when determining which points are local extrema. We're going to look for points where the second derivative is 0 to find all of the points that are in fact inflection points. So once we find these points where the second derivative is 0, to determine whether it's an inflection point, we do something very similar to the first derivative test. So we're just going to check whether that second derivative changes sign at the point p. So again, this is very similar to the first derivative test that we used for local extrema to find the critical points that are local minimums or local maximums. So here's an example of finding inflection points. Let's say we have the function f of x equals x cubed minus 9x squared minus 48x plus 52. So you might recognize this function from the last video. It's one that we already talked about. So first we're going to take the first derivative of the function, and we use the power rule a couple of different times to find that the first derivative is 3x squared minus 18x minus 48. And from there, we can take the second derivative. And the second derivative, again using the power rule, is just 6x minus 18. So using this inflection point test, the first thing we're going to do is find when the second derivative is equal to 0. So if we set the second derivative equal to 0, we find that 6x minus 18 has to be equal to 0, and if you solve this for x, you get x equals 3. So this is the only point of our function where the second derivative is equal to 0. This doesn't necessarily mean that the point is an inflection point. To determine that it's an inflection point, we have to look at the second derivative at a point to the left of that point and a point to the right of that point. So again, this is analogous to the first derivative test that we used in the last video. So we're going to pick a test point to the left of x equals 3. In this case, I chose x equals 2, and plug it into the second derivative. And we find that the second derivative is negative 6, which is less than 0 at that point. And then we can pick a test point to the right of x equals 3. So I chose x equals 4. And in this case, the second derivative ended up being positive. So we can conclude that the second derivative does in fact change sign from negative to positive at x equals 3, and since the second derivative changes sign, we get to conclude that x equals 3 is in fact an inflection point. So we took the second derivative and set it equal to 0 to find all of our possible inflection points, and then after we found those possible inflection points, we look at whether the second derivative is positive or negative to the left and to the right of that point to determine whether the second derivative changes sign. Okay, so here's another example for you of finding critical points and inflection points. In this case, f of x is going to be equal to x times e to the negative x. So the function that we're working with here is going to be a bit more complicated than the polynomial function from the previous example, but I think it's a good thing to see. So again, we're going to calculate the first derivative, and in this case, because we have x times e to the negative x, our derivative is going to require us to use the product rule. So this first term here, I get from taking the derivative of e to the negative x and leaving x alone, so I get negative x times e to the negative x. And then the second term I get by taking the derivative of x, which is just 1, times e to the negative x, which I leave alone. And then I can make this expression look a little bit nicer by factoring out this common term of e to the negative x, and I get 1 minus x times e to the negative x. So to find the critical points, we take this first derivative that we just found and we set it equal to 0 and we solve for x. So 1 minus x times e to the negative x equals 0 implies that 1 minus x is equal to 0 or e to the negative x is equal to 0. But in this case, e to the negative x is never going to equal 0 for any x. So we don't have to worry about this case where e to the negative x is equal to 0. And so we conclude that the only critical point we have is at x equals 1, because that's the only point where 1 minus x is equal to 0. Okay, so that answers the first part of the question. Now we want to find the inflection points of this function f of x as well. So to find inflection points, we take the second derivative, and again, we use the product rule. In this case, the second derivative gives us negative 1 minus x times e to the negative x minus e to the negative x, and again, we can make this expression look a little bit nicer, and it ends up being x minus 2, the quantity, times e to the negative x for our second derivative. So to find the inflection points, we take this second derivative and set it equal to 0. So x minus 2 times e to the negative x is equal to 0. And again, e to the negative x can never equal 0 for any x value. So the only possibility is that x minus 2 has to equal 0 for the second derivative to be 0 at that point. And this implies that x equals 2 in this case. So x equals 2 is the only point where the second derivative is equal to 0, and therefore the only possible inflection point. But to determine that x equals 2 is actually an inflection point and not just a point where the second derivative is equal to 0, we have to check that the second derivative changes sign at the point x equals 2. So I'm going to pick 2 points, one to the left of x equals 2 and one to the right of x equals 2, and verify that the second derivative does in fact change sign. So if I look at x equals 1 and plug it into the second derivative, I get something less than 0. If I look at x equals 3, I get something greater than 0. So because the second derivative changes sign to the left and to the right of x equals 2, we can conclude that x equals 2 is in fact an inflection point. So the full answer to this problem is that we have one critical point, and that critical point occurs at x equals 1, and we have one inflection point, and that inflection point occurs at x equals 2. Okay, and here is our final example for this section. So just another example of finding inflection points and saying some things about the behavior of functions using inflection points. So our question here is, what is the concavity of the graph of this function f of x equals ax squared plus bx plus c? So this is just the general form of a quadratic polynomial, and the graph of this function is always going to look like a parabola. So this is the general equation for a parabola in the plane. So if we want to determine concavity, we're going to look at the second derivative, but to get to the second derivative, we start with the first derivative. So in this case, the first derivative is just 2 times a times x plus b, and we get this derivative by using the power rule, or sorry, not the power rule. No, yes, the power rule, not the product rule, the power rule. And from here, we can take the second derivative. So the second derivative is just 2 times a in this case. And now we have the following observation. If a is greater than 0 in this expression, then the second derivative is also going to be greater than 0 for all x, because the second derivative is constant in this case. It's just 2 times a. On the other hand, if a is less than 0, then the second derivative is going to be less than 0 as well for all x. So here are the graphs in either of these cases. So if a is greater than 0, we end up with this graph on the left where our parabola is opening upwards. And if a is less than 0, then we end up with this graph on the right where our parabola is opening downwards. And this corresponds to what we should already know about parabolas, which is that the parabola opens upwards if this leading coefficient is positive, and it opens downwards if this leading coefficient is negative. So here's just a nice relationship, a way to relate our inflection points and second derivative and concavity to some geometric properties of parabolas that we should have seen before. Okay, so hopefully these examples are helpful for you and sufficient for you to get through the homework. As always, you can send me emails about the homework or comments about the videos, things that I can do better. Those are always appreciated, and I will see you in the next video.